Hello everyone. So today we will start our session week 11 on EPR spectroscopy. So EPR spectroscopy means EPR electron paramagnetic resonance spectroscopy, or we can say here electron spin resonance spectroscopy. You can say EPR also instead of ESR. ESR. Sorry, here ESR. ESR. Okay. So the primary condition for ESR spectroscopy is the molecule or ion or any species must have one or more unpaired electron. For example, hydrogen atom, oxygen atom, NO, NO2, carbon, radicals, transition metals. If the species will have unpaired electron, then only it will show EPR spectrum. Okay. So any electron while spinning, it will have a spin quantum number 1 by 2 and ms value is plus minus 1 by 2. Okay. So the magnetic moment associated with that spin can be given by this equation. Mu equal to minus G mu B by S, where Ge is called Lambda G factor. The value for Lambda G factor for a free electron is 2.0023. This is for free electron. What does it mean? Meaning in a molecule or in an atom, this value will change. So for free electron, this value is 2.0023, and this mu b is called Bohr magneton, which is given by this expression, E h cut by 2me, where E is charge on electron, h is like h by 2 pi, where h is Planck's constant, and m is mass of electron. If you will solve by substituting everything, you can use h cut equal to h by 2 pi. And when you will solve, you will get this value. Okay. So the magnetic moment associated with the electronic spin we can calculate using this equation. Okay. Now the energy associated with this electron spin can be calculated by using this equation. E is mu b dot bz. What is this bz? So we will come to this again. Okay, so we are leaving this part. So first we will try to understand here. So S is 1 by 2. Okay, and then ms is plus half. Ms can be plus half or minus half. Okay, ms can be plus half or minus half. If it's plus half, then we say alpha up spin. If it's beta, then we say beta down spin, and we will represent by this down arrow and this up arrow. Okay. So these two energy level will be degenerate. Degenerate means these two energy level will have same energy in absence of any magnetic field. Bz equal to 0. This Bz is magnetic field along z direction. Okay, and this is your energy axis. Okay. So but when you will apply the magnetic field, let's say you are applying some magnetic field B. Here you are applying some magnetic field B. So the splitting will happen. The splitting between alpha and beta will happen in such a way the beta will have lower energy than alpha, and this energy gap between alpha and beta will depend on the strength of magnetic field. Okay, so higher the strength of magnetic field, higher will be the separation energy. So this delta E. Now coming to, you will leave this part here, coming to this expression again. So when you will apply this magnetic field, so this magnetic field will interact with dipole moment, this magnetic dipole associated with electron, and it will give rise to this energy. So the energy can be calculated by this equation. Okay, so we can use this equation. Sorry, we can substitute mu from here. It will become like this. So here we introduce term ms. So ms can have two possible value. It can have plus half or minus half. If it will have plus half, then we saw here it's a alpha spin. If it's a minus half, then beta spin. So energy of this alpha spin is minus 1 by 2 GE mu B Bz. Okay, and the energy of this alpha spin, alpha state is plus 1 by 2 GE mu B Bz. So and the energy difference between these two states are this one. So this energy difference you can see directly related to applied magnetic field, because this is constant and this is also constant. So this is directly dependent on magnetic fields. So higher the strength of magnetic field, higher will be the separation, or higher will be the energy difference between alpha and beta spin. So you can write this as delta E is equal to h nu, correct? This delta E we know that is equal to h nu. So we can substitute here and we can calculate this frequency. This frequency is nothing but your Larmor frequency. Okay. So this frequency is the frequency required for the transition from beta to alpha. So here we understood from this slide, we understood what is the condition of EPR spectroscopy. What happens when electron spins, like it will associate with magnetic moment, how this magnetic moment interact with magnetic field, and how this give rise to the energy separation between alpha and beta state. Okay. So the next question is to take the transition before solving this problem. To let's say we draw the energy level this. So I will say this is alpha, this is beta. Okay. So in presence of magnetic field, the split is happen. Like this is your beta, this is your alpha. So to take this transition, we use radio waves. Sorry, microwave. Okay, we need microwave. We are studying in rotational spectroscopy also. In rotational spectroscopy also. We needed microwave. If you remember, then there also we need microwave. Similarly, for EPR we need microwave, but for NMR we need radio wave. So clearly we can say that this energy separation is higher in case of ESR or EPR than NMR. Okay. Now, based on the discussion on first slide, we will try to solve few problems. First is, the question is asking predict which of the following species will show EPR spectrum. Okay. So for EPR spectrum, the condition is the molecule or ion or radical must have one or more unpaired electron. So first is CH3. The first is CH3. So this is your methyl radical. You can clearly see it has one unpaired electron. One unpaired electron. And I will write one unpaired electron. Okay. So it will show EPR. I will say EPR active. Okay. EPR active. Instead of writing EPR active. Second question. CH2. So this is carbon. Okay. This is carbon. So there are two types of carbon. If you know correctly, there are two types of carbon. One is your singlet carbon and one is your triplet carbon. Okay. If you know the structure, it will look like this. The hydrogen. Okay. The hybridization is sp2 and you have this pz orbital. Okay. See, in singlet you will have one electron here and one electron here. Okay. So you can see clearly there are two unpaired electrons. But in case of triplet, if you draw the structure, you will get something like this. No unpaired. Here two unpaired electrons. So this will be your EPR active. This will not be EPR active. Okay. Now coming to third question. So we will add one slide here. Excuse me. The third question is methane. This is CH4. We call it methane. Okay. If you draw the structure of methane, there are no high unpaired electron, no unpaired electron. So this will be your EPR inactive. Okay. We'll see the fourth example. What was the fourth example? H2. H2 molecule. So any diatomic molecule you can understand on the basis of MOT, molecular orbital theory. So you can understand using MOT, molecular orbital theory. For H2, we will try to draw the molecular orbital theory diagram. So this is energy. So one. So this is your hydrogen. This is your also hydrogen. This is oneness orbital. The oneness orbital of other hydrogen. It will overlap and it will give your sigma oneness. And here also you will have anti-bonding. Sigma oneness star. This star will represent antibody here. So in hydrogen we will have one electron and this hydrogen have one electron. Okay. So bond order here will be 2 minus 0 to 2. So we can't see any unpaired electron here. Okay. From this molecular orbital diagram, we cannot see any unpaired electron. Okay. So this is your EPR inactive. I will change the color. So I will write EPR inactive. The next question is O2. O2. Okay. So again we will try to draw the molecular orbital of O2. Fifth O2. Okay. So we will try to draw the molecular orbital diagram. So you'll ignore the 1s. Okay. So let's say I'm writing that electronic configuration of oxygen atom. It is 1s2, 2s2, 2p6. So I'm ignoring this. I'm starting from here. Okay. So I'll write. So we will have here. So it has 2 electron. This is 2s, 2s. Okay, and here you have 6 electron. 4. It's a 4, not 6. Okay, here you have 4 electron. Okay, here you will have okay. So if you let's try to fill the electron. 2 will go here. 2 electron. Here 1. So we'll have total 8 electrons, so 2 will go here. So you can see here 2 unpaired electron. So in oxygen, in O2 molecule, we have 2 unpaired electrons. So that's why here we can cite atomic orbital of oxygen. This is molecular orbital of O2. And again, this is atomic orbital of O. So this is your EPR active. Similarly, the next question is, your sixth one is O2 plus. So you can take one electron here. Still we will have one unpaired electron. One unpaired electron. So this is also EPR active. Similarly, someone can ask O2 minus. So you can fill one extra electron here. So still you will have one more unpaired electron. So this O2 minus will also be EPR active. EPR active. The next molecule is your C6H6. C6H6. I am writing this is 8. C6H6. So this is benzene. This is your benzene. Okay. So we cannot see any unpaired electron here. See, all electrons are paired. There is no unpaired electron. So this is your EPR inactive. So from this discussion, we understood that the species or any molecules or ion or radical must have one or more unpaired electron. Then only it will show EPR spectrum. Then only it will give EPR spectrum. Okay. So from EPR, if we are doing EPR of some sample, and if we are getting some spectrum, then we can conclude directly that there must be some unpaired electron in the unknown sample. Okay. Now coming to the next question. Calculate the ESR frequency of an unpaired electron in the magnetic field of 0.33 Tesla, given that for the free electron G is this and mu is this. So the question is asking to calculate the magnetic field. Okay. Sorry, frequency. So we saw in the first slide the frequency expression was like mu equal to here mu equal to, it was G E mu B, and here this is your B divided by H. Here your B is nothing but your magnetic field. Magnetic field. Now everything is given. You just substitute the value. Okay, so value of G is 2 unitless. Okay, and mu B magnetic moment is 9.273 10 to the power minus 24 joule per Tesla. And how much magnetic field applying? 0.33 Tesla. And what is the value of Planck constant? 6.626 10 to the power minus 34 joule second. So this Tesla is cancelled out. This joule will cancel out. When you will solve the whole equation, you will get something 9 into 10 to the power 3 per second. Okay, this much you are getting. Okay, so you can write here your 9,000 hertz. No, sorry, you'll get something 9 10 to the power 9. Okay, so you can write 9,000 multiplied by 6. You can directly remove this. You can write this second inverse is nothing but your hertz, correct? So you can write 9 gigahertz. 1 gigahertz is nothing but 10 to the power 9 hertz. Okay. So it means this much frequency is required to take transition from beta to alpha when you will apply this much magnetic field. Okay. Now next slide. Which of the following is correct for ESR? So in the given option, which of the options or option is correct for electron spin resonance spectroscopy? Okay. The first is the frequency of ESR transition corresponding to radio frequency. Wrong. We saw in the first slide only, for transition to occur in ESR we need microwave frequency. Okay. The second question is correct. And we saw that there are two electron has two spin. Electron has two spin, alpha and beta, and we saw up and down. This ms value for this is plus half, and this is for beta is minus half. This is your ms. Okay. So beta, the value of beta is negative. You can see here, the value of beta is negative. Correct. So this is a correct option. This is MSQ question. So the multi-select question. Okay. Now, which of the following molecule cannot be used in ESR spectroscopy? So again, the similar question as the first question. So what is the condition? The condition is the molecule or a species or ion must have unpaired electron. So here we can see here the helium has 2 electron, correct? Helium has 2 electron, 2 proton. No unpaired electron. No unpaired electron. So this is your correct option. NO2 has 1 free electron. Similarly, copper 2 plus. So atomic number of copper is, so you can write the electronic configuration of copper. We will solve later. And this is your C6H5 radical. So it's clearly showing it has 1 unpaired electron. 1 unpaired electron. Correct. Now coming to the next question or next. So here in the previous discussion till now we understood like what are the condition for EPR spectroscopy, what are the factors on which the energy separation between alpha and beta spin will depend on those things, and we understood those concepts by solving few problems. So here we will see the width of ESR spectrum. So let's say transition is taking place from beta state to alpha state. So there is some absorption of microwave is taking place. Okay. Because of that absorption, you will get some absorption spectrum. So this is called absorption spectrum. Okay. And in NMR discussion, we saw that this broadness or width of the spectrum will depend on this relaxation time. We saw there that lower the relaxation time, higher will be the thickness or width of the peak. See, if you remember, the relaxation time for this ESR spectrum is lower than NMR. Okay. So if you will calculate this delta nu, it's higher than NMR. Like in solid state NMR, this relaxation time is lower than liquid state NMR. Similarly, this ESR for relaxation time for ESR spectrum is even lower than your NMR. Okay, so it will be broader than your NMR peak. Okay, so you will get some broad peak. So there is some advantages and disadvantages of this broad peak. Advantages is homogeneity of the magnetic field is less critical. Let's say you have bulk sample, you're applying magnetic field. So around at every molecule, it will almost every molecule will experience almost equal magnetic field. Okay, but what is the disadvantage? The disadvantage is to assign the peak position is uncertain. Like in this broad peak, we don't know where is the peak position, here or here. Okay, so you don't know where is the peak position. So then what can we do? What we can do, we can derive, we can make it, we can plot by using derivatives. Okay, so you will get something like this by second derivative, for derivative first derivative. Okay, so at maximum, this is your maximum value, correct? So at maximum, just dx dy by dx into 0 at maximum. So at maximum I can write dy by dx equal to 0. So using this condition you can find the peak position easily, correct? So by simply using derivative technique you can assign the peak position. Okay. Now we saw there that there was some factor gs there g. This is that Landau g factor. The value of this Landau g factor is 2.033, around 2.033. So here we do not consider any electron nucleus interaction like a spin orbit coupling. Then what will be the value of this in molecular system? It can change, it can vary. For example, in transition metal ions, the G can be calculated like this. G can be calculated using this equation, where it is given by Gi is your J quantum number. It is given by L plus S to L minus S. This L is nothing but your L. You can calculate this L to L plus 1 and S to S plus 1. So this thing you must have read in some coordination complexes chapter or lanthanide or actinide. There you will see this problem here. So there you can calculate the G using this equation. Okay, but this you can calculate. This will require some rigorous calculation, and if you can perform the EPR spectrum, that EPR spectrum of your coordination complexes, you will get some G value. Okay, and if your G value is different from this free electron value, then you can say that whether the spin orbit coupling is necessary or not. Let's say your G value is coming around 1, very far from this 2 value, or let's say you're getting some 5, or let's say you're getting some 10. So this is far from this free electron value, correct? So in this case, a spin orbit coupling will be important. So what is the conclusion? The conclusion is the EPR spectroscopy will help us in understanding whether the spin orbit coupling in metal complexes, coordination complexes, or lanthanide complexes is necessary or not. Okay. So based on this discussion, we will try to solve some more problem. Okay. The first question is in an ESR spectrometer operating at this gigahertz. So here what is given? Frequency, operation frequency. Your operation frequency is 9.233 gigahertz. Okay, so gigahertz means you can easily convert 9233 10 to the power 9 hertz, or we can write here 9233 10 to the power 9 per second. Okay. And center of the CH3 radical occurs at this millitesla. Calculate the value of G. Calculate the value of G for this radical, CH3 radical. Okay. So we know that this your H, your nu is nothing but your mu E, G E, I write B by H. So we have to calculate G, correct? G of electron. So you can write H nu divided by here mu A and beta. So we can substitute everything here. 6.626 minus 34 joule second. And what is the value of this? 9.233 10 to the power 9 per second. And mu is we saw in the previous calculation the value for this electron, this magnetic moment for electron, we got something like 9.273 10 to the power minus 24 joule per Tesla. And what is the B here? B is your, you're getting at what frequency? This one. So it's milli Tesla, so we have to divide by 1000, so you'll get something 3294 Tesla. So this your joule will be cancelled, Tesla will be cancelled, and your second will be cancelled, so unitless. So GE will be unitless, so you will get something like 2.0026. Little different from what is the value of free electron. Okay, now coming to the next question. Which valence state of copper, that is Cu plus or Cu2 plus ion, will show an EPR spectrum and why? Simple, you have to check the unpaired electron. Okay, so we will write the electronic configuration for both. So we know the Z29, Z means atomic number. So first we will write for copper plus. Say this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d9. Okay, so this is not the correct because of the reorganization energy. This one electron will go here and you will get something. So this is your incorrect one. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. This is for copper. Okay, for copper ion, for copper plus, so I write for copper. For copper plus, one electron will go out from this valence electron. Okay, valence electron. So we'll have 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. So from this electronic configuration of Cu plus, copper 1 plus, we don't see any unpaired electron. See, so there is no unpaired electron. Okay, so this will be your EPR inactive. Similarly, if you write the electronic configuration for Cu2 plus, so you will have similar, you will have D9 system. D9 means if you draw the this box configuration, 5 orbital, so you will have one unpaired electron here. You see, one unpaired electron. One unpaired. So this will be your EPR active. EPR active. Right. The next question. Summary, not next question, the summary. So till now we discussed the we just try to understand the conditions. What are the conditions, under which condition what will happen. Now we will see the interaction of this electron with nucleus, whether there is any interaction, how this interaction will take place, what will be the effect of the interaction between electron and nucleus. So we'll discuss those things here. So let's consider the free electron EPR. So So for that you will get some one single peak. Okay, there is only one energy level. There is only one energy level. See, if I draw for this, I will draw like so. There are two spin alpha beta. Both are degenerate in absence of any magnetic field. But when you apply the magnetic field, the energy separation will happen. Okay, this is your beta and this is your alpha. And because of this transition, you will get one peak. This is derivative, first derivative of this absorption peak. You will get something like this. Drawing is bad. Gets it like something like this, and by using first derivative, you will get some this peak, one peak. But interestingly, if you see the ESR spectrum of hydrogen atom, we are getting two peaks. One here, two here. Why two? Hydrogen has only one unpaired electron. Then why we are getting two peak in EPR spectrum of hydrogen atom? So if you see here, this is because of electron spin interact with nuclear spin. I am saying again, this electron spin is interacting with nuclear spin, and that we called hyperfine interaction. That we called hyperfine interaction. Okay. And this the strength of this hyperfine interaction is given by A. This constant A. Like higher the value of A, higher will be the strength of hyperfine interaction. So this for hyperfine interaction, we can calculate the hyperfine coupling constant. We will see later what is the hyperfine coupling constant, which can be given by A, Mi, Ms, H. This Mi is related to the spin of nucleus. This Ms is related to a spin of electron. So spin of nucleus we are considering plus half. The spin we are taking beta. Let's say beta. Okay, for beta state minus half, you will get something like this. Hyperconstant. Let's try to understand the physically why this hyperfine interaction is happening. Okay, so let's say we have nucleus here. So this we can explain with the help of quantum mechanics, not classical, because classical consider electron as particle. Okay, and particle rotates in a fixed circular path that we call orbit. Okay, but in quantum mechanics it's an electron cloud rather than particle. Okay, it's a wave nature. So electron cloud. Let's say we have nucleus here, hydrogen nucleus, and we have your electron cloud. This is your electron cloud. Okay, so I'll write here, this is electron cloud. Electron cloud. Okay. So at nucleus also, let's say I will write the z distance or x. At x equal to 0, probability of finding electron, probability of electron is not equal to 0. Even at x equal to 0, even at nucleus, the probability of finding electron is not 0. So that's why if the electron will present in s orbital, in that case, this hyperfine interaction is possible. But in case of p orbital, let's say for p orbital, okay, for p orbital, this is your nucleus, and let's say this is your p orbital. Okay, I'm writing only px. So at x equal to 0, at x equal to 0 we have node, see, node, and at node probability is 0. At node, this is your px I'm writing, px. So this is your plus, this is your minus. So at node, probability of finding electron is 0. So that's why the hyperfine interaction is not possible for P and D. Not possible for P and D, but it's possible for S. Okay. Next slide. For example, let's try to understand the energy level diagram for a hydrogen atom. Like how the energy level diagram will change after this hyperfine interaction. Okay, so in absence of any magnetic field, we saw previously also, these two level alpha up and beta down will be degenerate. When you will apply the magnetic field, that is beta not equal to 0, means we are applying some magnetic field. In that case, this energy level will split. Okay, this beta will have low energy and this alpha will have higher energy. So I write the reversed. Here it will be plus, here it will be a minus. Yeah. I wrote the reverse. Sorry, excuse me. Okay. But when it will interact with nucleus, this energy level will further split into two energy levels, plus half, minus half. And this strength of this interaction will depend on, I will explain in the previous slide also, this A, Mi, Ms, H. So for this case, let's say like this Mi has two possible value, plus half and minus half. Okay. So here plus half has low energy, minus half has higher energy. Similarly, this minus half, plus half. So if you first for this case, let's consider for this case. So the energy of this beta is 1 by 2 gs beta. I'm substituting mu b by beta. Okay, you can use the same. And there will be some additional term because of this hyperfine interaction. It will be ah by 4. H by 4. Similarly, you can see because of this additional term, the energy is decreasing. Okay. So there are two transition possible here in this configuration. If there is no hyperfine interaction, so there will be one transition possible. What you are seeing in case of free electron. But in case of hydrogen, there is one proton, there is a nucleus. Because of that nuclear spin, the nuclear spin will interact with electron, and they can have two transition possible. So from minus half to minus half, plus half to plus half. So from this transition, there are two transitions. We can see here, we will get two peak. Okay. So this is your magnetic increasing magnetic field strength. So you can see here, the separation between two peak, the separation between two maxima is called A. This is called hyperfine constant. We saw previously also hyperfine constant. This hyperfine constant is very useful in some aspects. We will see later. Okay. But one interesting thing we observed here, that transition is taking place between the same Mi value. Okay. So the selection rule, one primary selection rule will be transition within same value of Mi is allowed. So because of this hyper fine interaction between the electronic spin with nuclear spin, we are getting two peaks instead of one peaks in case of hydrogen atom. So this interaction, like we can simply like how many peaks we will get from some radical, how many signals we will get from some molecule. Those things we can understand with the help of this tree diagram. So what is this tree diagram? Let's try to understand. Okay. For a hydrogen atom, for a hydrogen atom, we have Mi 2 plus minus 1 by 2. So there are only two possible, okay? Two possibilities. So you will have like two peak with equal intensity. We can just qualitatively we can understand like this. For deuterium D, here ID equal to 1. So mi equal to your equal to plus I2 minus I. So you will have plus 1 0 minus 1. There are three possible values. Okay, three possible values mean you will get some three picks 1 2 3, and that this separation between two peaks is called A, hyperfine constant. Let's try to understand this CH3 radical. So here there are two atoms, carbon 12, we are considering carbon 12 and hydrogen. Okay, so for carbon 12 the I is 0, so this will not interact, like there will not be any hyperfine interaction between this carbon with this free electron. Okay, but this free radical, this free electron can interact with this hydrogen, correct? So with this carbon no interaction, carbon 12 no interaction, but with this hydrogen it can interact. How? So those things we can calculate using this equation 2ni plus 1. Here n is your, we can generalize here, n is your number of atom. Okay, so 2n, where I is 1 by 2 for hydrogen. Okay, so it will be a n plus 1 rule for hydrogen. Similarly, we saw in NMR, okay, number of peaks. So similarly, we can guess here also. So we can draw like this. See, one electron, then all the level will be degenerate. When you will apply the magnetic field, when you will have one hydrogen, so you will have two level. Okay, when you will have two hydrogen, you will have three level. With intensity 1:2:1. When you will have three hydrogen, you will have three peaks with intensity 1:3:3:1. So the intensity will change. So the intensity of all the peaks will not be identical. Okay. Let's try to understand with the help of this expression. So let's consider ms equal to minus 1 by 2. ms that is for beta spin. For beta spin. So we are considering four peak, like we are considering four situations. 1 2 3 4. Okay, and we are considering this proton 1, proton 2, proton 3. All proton we are considering just beta, sorry, ms mi plus 1 by 2. We are taking mi plus 1 by 2. Okay, correct. So these are the possibilities you can see here. These are the possibility and these are the energy levels. So here you can see there are only one way, means here you can see there are three ways. So the intensity will be 3. Here also you can see there are three ways. These things are discussed very well in the lecture note. I am just briefing it out. You can refer to the lecture note. So this will be the resultant EPR spectrum you will see for methyl radical, for CH3 radical. Okay. So this intensity means area of this peak will be, then the ratio will be 1:3. Now we will try to draw some EPR spectrum based on this discussion. Okay. So first is 1 for benzo semiquinone. 1 for benzo semiquinone. So the structure of this benzo semiquinone is this one. Oxygen here, oxygen here. Okay. Here you have minus. So number of unpaired electron. Number of unpaired electron is 1. Number of unpaired electron बराबर 1. एक है, ठीक है? So, and but there are 4 hydrogen here. 4 hydrogen. Okay. And let's say all the carbon is C12. Okay. No C13. We are assuming that assumption. because for C13 we don't have I equal to 0. So in that case, this free radical will interact with C13 also. So that's why for to make it less complex, we are assuming this assumption. We're taking this assumption, okay? So there are four hydrogen. There are four hydrogen, and for each, like your Mi is I is 1 by 2. I is 1 by 2. So the Mi, or we can write here Mi is like summation of all the four. So it will be 2. Okay, and your capital Mi will be your um, plus 2 plus 1 0 minus 1 minus 2. There are 5 possible values. Okay, so we'll try to draw here the spectrum. There are two level here. Okay, this is alpha, this is beta. I will write, or I will write plus minus half. Okay. In absence of any magnetic field, these two will be degenerate, and after that it will split like this. Okay, so this is your plus 1 by 2, this is your minus 1 by 2. Okay, now when this hyperfine interaction will happen, like here the Bz is not equal to 0, but here hyperfine interaction is 0. There are no hyperfine interaction, but when the hyperfine interaction will happen, and this level will split into 5 energy level. How? Because of the n plus 1 rule. We have 4 hydrogen, hyperfine line, so we can say hyperfine line is n plus 1. Okay, so 4 plus 1 is 5. Okay, so this will go here and here, then up, and one energy level will not change, so you'll have 5. This is plus 2 plus 1 0 minus 1 minus 2. Okay, similarly we'll write here okay, this is minus 2 minus 1 0 plus 1 plus 2. Okay, this is your Mi value, all the values Mi. So what did I mention? The transition between the same I value will be possible. So first transition will be your from here to here, second transition will be from here to here, third transition will be from here to here, fourth transition will be from here to here, and fifth transition will take place from here to last one. So there will be 5 transitions, so you will get 5 peak. And what will be the ratio, what will the intensity ratio? So that thing we can decide with the help of coefficient of the binomial or using Pascal triangles. Okay, how? Excuse me. So how? Let's try to understand with the help of binomial. So 10 to the power 5, because there are 5 peaks, so we will write 10 to the power 5. write the binomial coefficient, it will be 8 to the power 5, then 8 to the power 5, 8 to the power 4, b, then we will multiply 5 with 4, it will be 20, and then we will divide with number of terms. So 2, it will be 10, a 3, b 2, plus 30 divided by 3, 10 a square b 3, plus 10 to the 20 divided by 4. So we will have 5 a b 4, and then b 5. So coefficient is 1, 5, 10, 10, 5, 1. So if you draw the intensity, sorry, excuse me, so you have to write 4, 1 minus here. So a4 would be 6 a square b a square 4a bq plus b4. So 1 is to 4 is to 6 is to 4 is to 1. Sorry. See, if the we are getting 5 transitions, then we have to write a to the a plus b to the power 4. Sorry, excuse me. So if you draw the spectrum, try to draw the spectrum. So we will get something like this: 1, and then 4, 4, and then 6, 6, and then again 4, and then again 1. So this is your 1 is to 4 is to 6 is to 4 is to 4. This is your experimental spectrum. Okay. Now coming to the next question. The ESR spectrum of a radical having empirical formula C3H7 radical. Okay. Showed 14 lines with relative intensity 1 is to 1 is to 6 is to 6 is to 15 is to 15 is to 6 is to 6 is to 1 is to 1. This must be. Identify the radical. Identify the radical. So how many peaks is giving? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total number of peaks is 10. Lines. Total number of lines. So we'll solve this later. Now coming to the next question. Now we saw there that this hyperfine constant, this A is hyperfine constant. So this is related to electron density of unpaired electron. So this you can say that this hyperfine constant A is directly proportional to electron density of unpaired electron. Unpaired electron. Okay. So if you remove this proportionality sign, you'll get something like this R rho. For hydrogen atom, this R is 0.05 Tesla. So this from experiment, this A you can calculate. This this is experiment from experiment, experimentally determine. Okay. And from this experiment, if you get the A, you can calculate this one can be calculated the electron density of unpaired electron of unpaired electron. Okay, we'll come to this later. For example, let's say we have hyperfine constant in the ESR spectrum of naphthalene minus. Okay, so this is your naphthalene minus. So we will try to draw the structure of naphthalene first. We will draw like this. So this is your naphthalene, and you have naphthalene minus. So this position we call alpha, and this position is called beta. Okay. The R value, at alpha and beta, at alpha the R is equal to the hyperfine constant at the alpha and beta position. This is not R, sorry, something is wrong here. This is not R. This is your A. A is 4.59 millitesla at alpha and 0.183 millitesla at beta. So this also you can say like electron density alpha position is higher than beta. Okay. Now let's try to write this equation. H sorry A is equal to R rho. Okay. rho. And we know here that R is for hydrogen atom, we know that R is something 0.05, so you will consider that R is your 50 milli Tesla. It was 0.05 Tesla, so I multiplied by 1000. So here you can calculate rho at alpha and at beta rho. So you can write here rho A by R, that is 0.18 49 milli Tesla by 0.050 milli Tesla. So this will be cancelled and your electron density will be unitless. So you will get something like 0.22. Similarly, you can calculate this A by R, you will get something 0.08. So here 0.22, this one is 0.8, 0.08. So what we can say, the electron density at alpha position is higher than beta position. Now coming to next question, a free radical containing two equivalent protons gives a 1:2:1, 3 lines in the ESR spectrum. The lines occur at the magnetic field intensity this. Calculate the hyperfine coupling constant. So we will draw the spectra here. So 1:2:1. So here 1, 1:2:1. Okay. So this is increasing electromagnetic field B. So this one is 330.2 millitesla, and this is getting at 320.5 millitesla, and this one is at 334.8 millitesla. And what is the hyperfine constant? The hyperfine constant is difference between two peak. Okay, difference between two peak. So the hyperfine constant A, let's say we are calling this B1, this is B2, this is B3. So this hyperfine constant should be B2 minus B1. This must be equal to B3 minus B2. So you can calculate B2 minus B1. Okay. So 332.5 minus 330.2 millitesla. Correct? So you get something 2.3 millitesla. Similarly, you can calculate B3 minus B2, you will get something 334 minus 8, 332 minus 5, this is millitesla, and this will be equal to 2.3 millitesla. This gap, the gap between two peaks is 2.3 millitesla, and this gap we call it hyperfine coupling constant. Okay, so by solving this problem, we are stopping this lecture here, and this EPR lecture is still not finished, so we will solve more problem in the next week. Thank you.